Hello everyone and welcome back to your YouTube channel. And welcome to this very interesting video today. It's a very practical, very simple and very short video. In recent time, I received so many people asking me about obtaining the system matrices using DIgSILENT PowerFactory. What I'm telling you is that people, especially people coming from the control system background, they are interested to obtain the state matrix and the matrix B, C, and D together from the small signal stability command functionality inside DIgSILENT PowerFactory. So as I receive so many times these requests, I decide to record this very short video. And what I will do today is I will start with a very important background and explaining the state variable model and the state representation of a dynamic system. And then I will show you the way that DIgSILENT PowerFactory is modeling the dynamic system in order to perform the modal analysis. Then I will go inside DIgSILENT PowerFactory using one of my classical examples, and there I will show you how to export the system matrix and some other matrices, okay? But before we start, I will do the same as usual. I would like to suggest that you follow me at ResearchGate, because over there you will find all the slides, presentation, and scientific papers that we are doing right now. Today we are using one of the examples, classical example inside my YouTube channel, and this example is completely free and you can download that from the GitHub repository. Also, if you are watching this video, is because you are in your YouTube channel, and I highly suggest that leave a comment over there, a question. I will be extremely happy to help you. If you are interested to follow what we are doing in terms of research, development, and innovation, I highly suggest that you follow some of my social media accounts, specifically LinkedIn and Twitter. Finally, some people ask me for an email address in order to contact me. So here at the very bottom of this slide, you will find my email address. Well, but without further delay, let me start a very short explanation about the state space model, okay? When we are working in dynamics, when we are working in dynamic system, and remember, electrical power system is one of the dynamic system, we can use the differential algebraic model to represent the dynamics of the system. However, people coming from the control theory background and also some power system control guys, they love to use the state space representation. The state representation, what it's doing is basically using the continuous time variant representation, where we have the derivative of the state variable, we have the input variable, we have the output variable. What I am trying to tell you is that between the input and the output and the state variable and the derivative of the state variable, we use 4 matrices to create the connection and the interaction. Those 4 matrices are A, B, C, and D, using the 4 letters from the alphabet, where the state matrix A is basically probably the most important matrix from the power system small signal stability point of view, because the state matrix is the matrix that is used for the modal analysis. We calculate the modes, basically calculating the eigenvalues of the state matrix. Then we have here the matrix B, that is also called the input matrix. We have the C matrix, that is the output matrix. And we have the matrix D, that is sometimes called the feed-forward or the feed-through. However, this is a time domain representation. And this time domain representation for small signal stability, we use a new version of this representation. what we do is typically create a linearized version of this state space representation. And to do so is extremely simple. We say that the power system is operating in an equilibrium point. So we have an initial state and initial input. And from there, we use a small deviation, or what we call a disturbance, in order to create a small deviation in the system. Then what we do is that the nonlinear functions f(x,u) is represented using the Taylor series expansion. What I am telling you is that we are departing here from the differential algebraic equation model, and we are obtaining the linearized model. Again, inside the linearized model, we have the matrix A, B, Z, and D, okay? This is basically a very short explanation about how the small signal analysis is performed, and is basically using the state matrix that is basically the matrix A. If you want to know more about this, I highly suggest that you go back to the YouTube channel, and here there is a link, and you can watch this video that was created with my colleague, Dr. José Luis Reda from Technical University Delft in Netherlands. It's a 1-hour video, and my colleague José Luis, he explained completely the theory, but also presents some examples using what we call DIgSILENT PowerFactory. Also, I have a video in the YouTube channel that you can see is around 30 minutes with more specific oriented detail for the DIgSILENT PowerFactory model analysis, and also I performed the comparison between the model analysis and the time domain. And today, for the practical use, we are using one of the test system that is very well known in the YouTube channel, and is the test system number 5. It's basically a single machine infinity bus bar. Is the test system number 5 that we use in some other videos. If you want to get that, go to my YouTube repository, my GitHub repository. Here at the top, you can see the link, and from there you can download the project and import into DIgSILENT PowerFactory. Another thing that I want to clarify before going into the practical area is that inside DIgSILENT PowerFactory, we have access to the system matrices, but it's very recent. If you go to the very old and is already no include and supported by DIgSILENT PowerFactory, if you go to the version 15.1.7, as you can see over here, this very old version, there is no possibility of exporting the state matrix. However, version 2020, 2023, they allow you to export the system matrices. Today, we are using the version 2020 for the practical example, okay? But before I present the practical example, I would like to clarify something. In the previous slide, we used the state space representation. However, inside the DIgSILENT PowerFactory is used another representation that is very, very important, because it's connected with the way that the DIgSILENT PowerFactory is creating the models, the system models, but also the way that they allow us to integrate models. As I say before, dynamic systems, they are represented by differential algebraic models. However, here we have the differential algebraic equation model that you can find inside the DIgSILENT PowerFactory. In fact, you have a state vector, and inside that state vector we have n for November state variables. And we have the vector v for Victor, and inside that we have m algebraic variables. And what I'm trying to tell you is those algebraic variables, v, they are coming from elements like the passive power network variables, and also for the control variables inside the DSL models. So what is important is that Inside the 𝐷IgSILENT PowerFactory, they linearize the model using a numerical approach. This numerical approach is basically combining the control and passive power system, and they are represented for this equation. Let me put over here, this is the equation number 1. Inside this equation number 1, you will identify that on the right-hand side, we have the incremental quantities for the state variable and for the algebraic variable. And on the left-hand side, we have the incremental quantities for the derivative of the state variable and the algebraic variables. Here, we found a very important matrix. It's a coefficient matrix. This matrix has 4 submatrices, and this is what we call the Jacobian. The Jacobian is basically identical to the Jacobian that we use for the lot flow calculations. And on the left-hand side, you can have the identity matrix and the M2 matrix, okay? What is important is that you understand that here we are not having the same representation using the matrices A, B, C, and D. But using very basic calculation, we can call the coefficient matrix on the left-hand side M, and we can call the coefficient matrix on the right-hand side, the Jacobian matrix J. From there is very simple, because from there what we can do is to obtain the state matrix. And over here you can see that this is the state matrix. It's a numerical matrix, and all the terms that you require to define the state matrix are basically terms based on the Jacobian matrix. So what I am trying to tell you is basically that the state matrix is created numerically inside PowerFactory, is based on the Jacobian, and this matrix represents the state matrix. However, for my people that they were asking me about the matrix B, C, and D, I have very, very bad news. Because for now, version 2023, the input matrix B, the output matrix C, the feed-forward matrix D, that they belong to the state space representation, they are not used for the linearized power system formulation inside PowerFactory, so they are not available inside the model analysis calculation. So I really sad to be the person to tell you that those matrices are not included. However, all this information can be found just reading. As usual, I highly suggest people to read what we call the user manual of PowerFactory. However, on the other hand, the good news is that inside the 𝐷IgSILENT PowerFactory, there are several matrices that we can obtain. And one of them, as I said before, is the state matrix. But also we can export the eigenvalue, the left and right eigenvectors, the Jacobian matrix, the M matrix, and the participation factors. So again, the 𝐷IgSILENT PowerFactory provides this model analysis function, and this allows you to obtain numerically and in a very good way for the MATLAB format the state matrix. Well, now what I will do is I will go inside the 𝐷IgSILENT PowerFactory, and there I will show you how to export those matrices, okay? Let's go to PowerFactory. Well, here we are inside the 𝐷IgSILENT PowerFactory, and you will identify this is a very well-known test system inside the YouTube channel. This is a single machine connected to an infinity bus bar using a transmission system. In this case, a step-up transformer, 2 transmission lines in parallel, and finally we are using an ideal AC voltage source to represent the infinity bus bar. The first step to show you is I will calculate very quickly the lot flow, and you can see that we get the same results that you can find in the YouTube videos inside the channel. What I will do now is, again, here you have access to all the commands, calculation functions inside the 𝐷IgSILENT PowerFactory. We select here the model and eigenvalue analysis, And here at the very top, you will find this icon that is basically to configure the study from the modal and eigenvalue analysis. Here we have the basic option. Here you see the calculation method. We will not change anything here, but you need to recognize that we are using the 𝐻𝐸 method, okay? What is relevant for us right now is that we have here a tab for the output, and the very first option that you can see over here at the top is output to MATLAB files. I click here and I will be exporting the system matrices. And what you need to do is define a directory or a path inside your computer in order to the files be stored over there. I select here the full detail output, and also I use the default settings for the remaining functionalities. Right now what I will do is execute, and as you can see over here, PowerFactory is talking to me and is telling me that the computation of the eigenvalues and eigenvector is done, and you can see that the system dimension is 7 state variables with 30 lot flow variables. The dimension for the eigenvalue of the problem is 7, and after using the QR algorithm, we get that one of the calculated eigenvalues is not recorded. What I will do now is I will show you a plot for the eigenvalues. Select here model and eigenvalue analysis, then select a plot for the eigenvalue plot. And now PowerFactory is asking me for the configuration. I will use the default, green for stable and red for unstable. Then, as you can see over here, probably it's very difficult for you, but this is the mode number 1, this is the mode number 2, 3, 4, 5, and 6. If you want to see this in a table, there is a button here, and I will say, please show me a table with the results of the modal analysis. It's very clear that here in this table we have 6 modes, because as I said before, one of them is outside the recorded limits. And here clearly we can see that there are 2 oscillatory modes, mode number 2 and number 3. And as you can see, when they are oscillatory, you can see the damping frequency and the damping and damping ratio, okay? Well, but now what is very relevant for us is to see the output matrices, the system matrix, using the MATLAB program. Well, here we are. This is a folder, and inside this folder we have 4 different files that I obtained directly from PowerFactory. The first one here on the right-hand side is basically a text file, and in this text file you can see the names of the different variables in the system. You can see here we have 7 state variables, we have the voltage variable, we have the current variables, and the output signals. When we are here at the very top, we can identify there are 6 state variables, and those 6 state variables, they are related with the electromechanical model of the synchronous machine. As you can see, 4 of those states are related with magnetic flux. You can see over here 4 related with electromagnetic. Then we have phi and speed, and those are the representation for the rotational speed and internal angle of the machine. And finally, number 7 state variable is related with the AC voltage source, and this is the phi u, okay? Now what I will do is just I will double click here the matrix, and this is the state matrix that we obtained from DIgSILENT PowerFactory using the command for modal analysis. And right now MATLAB is opening, and I would like to have a look inside this MATLAB file, where we can find specifically, we can see here the state matrix, okay? Let me open the state matrix for you, and it's extremely simple. And well, here we have the 7 by 7 matrix, and this is the 7 by 7 matrix representing what we call the state matrix, okay? This is the matrix A. If you want to calculate the eigenvalues of the system, what you need to do is using the eigenfunctionality inside the MATLAB, and you will get the same result, the same eigenvalues that we obtain using the DIgSILENT PowerFactory. So right now I show you that yes, you can export the system matrix, but the matrix that you can get directly from the model analysis is the state matrix. I am sorry to tell you, but the matrix B, C, and D, they are not available, at least to the current version of the DIgSILENT PowerFactory. They are not available for the users, okay? And this is related with the way that PowerFactory is calculating the linearized model, okay? Well, this is the end of this video. In this video, I try to explain or try to answer one very useful question for many people regarding the system matrices inside the DIgSILENT PowerFactory. And just to conclude, in this video, I show you the state space representation. That representation is where you can find matrices A, B, C, and D. But inside the DIgSILENT PowerFactory, for several practical reasons and the way to obtain the numerical state matrix, you are able to obtain the matrix A, the state matrix. Regarding matrix B, C, and D, well, I am afraid that they are not available, at least at the version 2023 of the DIgSILENT PowerFactory. However, you don't need this video, because if you read the user manual, you can clearly read over there that the state matrix is the only available, and B, C, and D, they are not. Well, this is the end of this video. I hope you enjoyed this video. If you enjoyed, please subscribe to the YouTube channel and also leave us a message in order that we can answer your question. Thank you very much for watching this video, and I will see you at the next one. Bye now.